In this lecture, we're going to wrap up chapter 1 and we're going to cover section 1.7, which is linear inequalities and absolute inequalities. So first, let's look at solving an inequality. You guys probably have solved an inequality at some point, right? Instead of an equation, the expression has an inequality, whether it's less than, greater than, less than or equal to, or greater than or equal to. So when we solve an inequality, it's the process of finding the set of numbers that make the inequality a true statement. These numbers are called the solutions of the inequality, and we say that they satisfy the inequality. And the set of all solutions is called the solution set. Now, it's impossible to list every single solution that's part of the solution set. So we either write, we express our answer in interval notation or in a number line, or we could use set builder notation. So before we actually solve an inequality, let's review interval notation. So we have two types of intervals. We have open or closed. An open interval does not include A and B. So if my interval is going to go from A to B and it's open, A and B are not included, but everything in between is. So the way we would write the set A to B, not including A or B, would be what I just highlighted in yellow. So we would write A comma B and put open brackets around it. So it's like the soft parentheses. The other notation that we could use is what's called set builder notation, which I'm circling right now. So we use the set brackets, these little squiggly brackets, and we say all values of X such that, so this vertical line means such that X is between A and B, right? Because we have two inequality signs. So really what we're saying is X is greater than A, but less than B and not inclusive because these are strict. If we were to use a closed interval with the square brackets, that represents the set of real numbers between and including A and B. So here, this interval goes from A to B, including A and B. And then we could also use set builder notation where this reads all values of X such that X is greater than or equal to A or less than or equal to B. So everything in between, including A and B. Now, sometimes we have the infinite interval, which represents the set of real numbers that are greater than A or let's say less than B. So this one says A to infinity, right? So anything greater than A, but not including A, all the way towards positive infinity. Now, whenever we use the infinity symbol, we always use the open set. So if we were to go from A to infinity, not including A, this is how we would write it in interval notation. And if we were to use set builder notation, we would say all values of X such that X is greater than A. The other infinite interval is negative infinity to B. So it's the set of real numbers that are less than or equal to B. So everything from negative infinity to B, including B, if we had this square bracket around it. And if we want to write it in set builder notation, we could write all values of X such that X is less than or equal to B. So down here, I just put a little note. Parentheses indicate endpoints that are not included in the interval, and the square brackets indicate endpoints that are included in the interval. And anytime we're going to state positive or negative infinity, we always use the parentheses, never the square brackets. So let's just practice. Before we solve any inequalities, let's just practice using interval notation. So for example 1, let's just express each one of these intervals in set builder notation, and then we'll just graph it on a number line. So A says -2 to 5. The square bracket is around -2, so -2 is included. There's an open parenthesis on 5, so 5 is not included. So if I was going to write set builder notation, we would write it as all values of X such that x is greater than or equal to -2, since 2 is included, but less than 5, since we're not including 5, because there's an open parenthesis on 5. And if we were to graph on a number line, if this is 0, let's say here's 5, and then here's -2, we would have a closed circle on 2, because remember, the closed circle includes the endpoint, and then we would have an open circle on 5, and then we would shade every value in between. So this is what the solution set would look like on a number line. We would shade in between. The other way sometimes we might see this also is, instead of using the open and the closed circle, we can also use the actual bracket or parenthesis on the graph. So you see how on the left side, -2 is included. So I'm putting a square bracket on the -2, and then I'm going to shade all the way to 5, but I put an open parenthesis on 5. So that's another way you might see it graphically also. So let's look at the next one. So the next one is from 1 to 3.5, square brackets, so both are included. So in set builder notation, we're going to say all values of x such that x could be greater than or equal to 1, but less than or equal to 3.5. And if we were to put this on a number line, so here's 0, here's 1, here's 3. Let's say this is 3.5. So we're going to go from 1 to 3.5 inclusive, and we're going to shade everything in between. So let's do one more. What about C, which is the interval -infinity to -1? So in set builder notation, we would say all values of x such that, now x could be anything from -infinity to -1. So another way of saying that is everything less than -1, right? So all values of x such that x is less than -1. So that's what our set builder notation would look like. And if we want to put it on a number line, if this is 0, this is -1, we're not including 1, so I'm going to have an open circle on 1, and we want to shade everything less than, all the way towards -infinity. So we're just going to put an arrow that indicates that that shading is going to continue all the way towards -infinity. The other thing that I want to review is intersections and unions. Excuse me. Unions we're going to use, here and there to join two sets. Intersections are important too. So let's go over the difference between the two, and then we'll just do an example, and then we'll go to solving inequalities. So example 2 says find the set from 1 to 3, and then intersection 2 to 6. So just a reminder that this upside down U is intersection, and it means end. So we're joining the two sets. Or you know what I'll say? It's end, and we want to think both. So where both sets overlap. And then U is union. That means or. And we're going to join both sets. So we're going to join them together. And I'll show you what I mean when we do example A and B. All right, so let me just make room. Let me get rid of this. And just a reminder, these are videos. So even though I might erase, you could always pause at any point in these videos in order to finish copying something down. All right, so find the set 1, 3, intersection 2, 6. So in other words, we want to find where the sets happen at the same time, where they overlap. So I think the easiest way to do this is draw a picture. So here's 0, 1, 2, 3, 4, 5, 6. Here's -1, -2. So first, let's sketch the set 1, 3 on the number line. So 1, 3, and it's square brackets, so they're included. So I'm going to put a closed circle on 1, closed circle on 3, and I'm going to shade in between. Now in red, I'm going to sketch the interval 2 to 6, but the 2 and the 6 are not included, right? So I'm going to do open circle on 2, open circle on 6, and I'm going to sketch all the, solutions in between. Now we want the intersection. So where do these sets overlap? Where do they both happen at the same time, in other words? So you see it's this area right here that I just colored in red, right? Because it had red and blue. So it's going to be everything from 2 to 3. But now we have to think about, what do I put on the 2 and the 3? And you know what? Let's make this a little bit bigger. I'm just going to space this out a little bit just so we could see a bigger overlap. So we had from 1 to 3, and that's in blue. Now in red, we're going from 2 to 6, both open, because 2 and 6 are not included, but then everything in between is included. So now what we want to do is we want to find, where do they share common solutions? That's the intersection. So it's here, right? You see this overlap of the red and the blue. So now we have to write that interval. And we said, okay, that goes from 2 to 3. Now we could see it better in this picture. But the 2 is not going to be included. The 2 is going to be open because you see how the 2 is open on this set. So it has to be included in both sets. So there's no overlap at 2 because 2 is open, but as soon as we go to the right of 2, everything is included. You see that overlap between the red and the blue? Up into and including 3, because 3 is included in both sets. So I'm going to put a square bracket around 3. So that would be the intersection of the sets 1, 3 and 2, 6. So now let's find the union of the two sets in B. So union is joining the two sets together. They don't have to share common elements. We just join the two sets together. So let's look at this example on the number line. So we have 0, here's -3, we have 1, 2, 3, 4, 5. So the first set goes from 1 to 5, not including 1, right? So I'm going to have open circle on 1, closed circle on 5, and I'm going to shade everything in between. Now for the other set, we have from -3, including -3, up to 2, not including 2. So it's going to look like this. So this is not the same thing as intersection. Remember, like in A, intersection is where the two solutions, like where the two sets overlap and have common solutions. The union is just join the two sets. Take the red set, take the blue set, join them together. And you see from -3 to 5, everything is shaded, right? Even though for one interval, it only goes from -3 to 2 open, and then the other interval goes from 1 to 5, not including 1. 1 is included in the other set, right? So everybody's included somewhere. There's no breaks in this shading in the graph. So the union of the two sets is going to go from -3 to 5. And 3 is included, right? We have the closed circle on 3, so I'm going to put a square bracket, and then 5 is also included. So I'm going to put a square bracket around the 5. And that would be the union of those two sets. We're just joining them together. And you'll have more practice on the homework assignment with this. But the reason I'm practicing this is because now whenever we solve the linear inequalities, we're going to write our answers in set notation, either set interval notation or set builder notation. So I just wanted everybody to be comfortable with that. So let's solve a linear inequality in one variable. So we said earlier that the difference between a linear inequality and a linear equation is the symbol, right? Equation has an equal sign and inequality has an inequality. And just a quick reminder, remember, this is less than, this is less than or equal to, this is greater than, and then this one is greater than or equal to, right? So the difference between your four inequalities. So here we have ax plus b is less than 0. Here we would say ax plus b is greater than 0. Here we would say ax plus b is less than or equal to 0. And then here we have ax plus b is greater than or equal to 0. So in general, when we multiply or divide both sides of an inequality by a negative number, the direction of the inequality symbol is reversed. And that's really the only difference between the steps when we solve for an equation versus solving for an inequality. The steps are going to be the same as when we were solving linear equations, but the only thing you have to keep in the back of your head is that when we're solving inequalities, if we multiply or divide both sides of the inequality by a negative number, we have to reverse the direction of the inequality. So let's practice. So let's look at example 3. So A, we have 2 minus 3x is less than or equal to 5. So same steps as if we were solving an equation. Isolate the variable term. So the first thing I'm going to do is subtract 2 from both sides. So I'm going to get negative 3x is less than or equal to 3. Now, in order to get 1x, we have to divide by negative 3. So we're going to divide both sides by negative 3. But this is what I was saying earlier. Since we're dividing the inequality by a negative number, we have to reverse the direction of the inequality. So we're going to have x Now let's reverse the direction of the inequality is greater than or equal to 3 divided by -3, which is -1. So on a number line, in order to represent x is greater than or equal to -1, we're going to put a closed circle on -1, and we want greater than or equal to. So we're going to shade all the values to the right because they're all greater than. And we're just going to put a little arrow indicating it's going to go, the solution set's going to go all the way towards positive infinity. Let's also practice writing this in interval notation. So we're going from -1 to positive infinity. So -1 comma infinity. -1 is included. So we're going to do a square bracket. And remember, it's always a parenthesis around infinity. So that's how I would write my answer in interval notation. You always want to check your answer. So the way we could check is pick any numbers that fall within this interval, right? So like look at 0. 0 falls in this interval. So let's plug it back into the original. 2 minus 3 times x, but let's replace 0. 3 times 0 is 0, and 2 minus 0 is 2, and 2 is less than or equal to 5. So pick some numbers that are in the interval, make sure they check out, then pick a number that's not in the interval and plug it into the original, and it shouldn't make a true statement. So that's how we could check our answers. So let's look at B. So in this case, we have to first distribute. So we're going to get 2x plus 8 is greater than 3x plus 2. Let's gather the x terms together. So I'm going to subtract 2x from both sides. So I'm going to bring the x terms to the right, which then means I have to bring the constant to the left. So I'm going to subtract 2 from both sides. So we're going to have 6 is greater than 1x, or just x. Now, it's kind of weird when the x is on the right-hand side of an inequality, because usually we like to say x is, and then, whatever the inequality is and whatever that endpoint is. But we could just rewrite it where the x comes first, right? So this is the same thing as x is less than 6, right? Because look, you see how in the inequality, the arrow's pointing towards the x and it's open towards the 6? It's the same thing. X is less than 6. So if I were to put this on a number line, x is strictly less than 6, not including 6. So I'm going to put an open circle on 6, and I'm going to shade everything to the left. And let's also practice interval notation. So my solution set is anything less than 6, right? So everything towards negative infinity. So in an interval, I could write it as negative infinity to 6 and open bracket, right? So it's going to be an open parenthesis on both because 6 is not included. And in C, we have what's called a compound inequality. So anytime we have two inequalities in one of these expressions, so like the other two we did just had one inequality, right? This one has two. What we do is when we solve for x, get 1x in between the two inequalities. So isolate the x in between the two inequalities, get rid of the constants, but now we're going to have to make sure we bring to both sides, because we have kind of two sides, right, of this inequality. It's a compound inequality, but the steps are going to be the same. So look, I want to isolate the 2x. So I have plus 3. So if I subtract 3, I got rid of the 3, right? But then I have to subtract 3 from both sides of the inequality. So 1 minus 3 is -2, less than or equal to 2x, is less than 11 minus 3 is 8. Now we have 2x, right? But I want 1x, so I'm going to divide by 2. But then we have to divide everybody by 2. So I'm going to have x is greater than or equal to -1 and less than 8 divided by 2, which is 4. So x could be anything from -1 to 4, including -1. And on a number line, we're going to go from -1 inclusive to 4 open, and it's going to be everything in between. And if I wanted to write this in interval notation, we're going to go from -1 to 4. We're including -1, so close bracket on the -1, and we're not including 4, so it's going to be an open bracket on the 4. So that's how we solve an inequality or a compound inequality, and that's how we would represent answers on a number line and interval notation. Sometimes we might see an absolute value in the inequality. So if you look at example 4, I still see the inequality signs, right? The symbols, but now in each one, I have an absolute value statement. So how does that work? So I wanted to start by showing you an example on the whiteboard. So let's go over to the whiteboard for a minute. So let's say, for example, we had the absolute value of x is less than 2. So we want to solve for x, right? So the absolute value of what number or numbers is going to be strictly less than 2. So let's look at this from a visual perspective, right? Let's look at the number line. So here's 0, 1, 2, 3, -1, -2, -3. Now remember, absolute value represents the distance from 0 on a number line. So what we're saying is we want the absolute value of x, which is the distance from x on a number line, to be the distance from x to 0 on a number line. We want it to be less than 2. So from 0, we don't want to go any more. We want it to be the distance to be less than 2. So we don't want to go any further than 2 in either direction, right? A distance of 2. So that's going to land me at +2 and -2, right? So anything in between. So for example, -1 is in between, right? What's the absolute value of -1? It's 1. And 1 is less than 2. Let's pick 0. The absolute value of 0 is 0. 0 is less than 2. Every single one of these numbers between -2 and 2 has a distance less than 2 from 0. So they're all going to check out. But since it's strict, right, there's no equal to sign underneath this inequality, we're not including -2 and 2. Now, look what would happen if we picked 3. The absolute value of 3 is 3, but is 3 less than 2? No, right? So nothing beyond -2 or +2 is going to be part of the solution set. So my answer is all values of x that are between -2 and +2, right? Or we could write it in interval notation, -2 to +2. So the way we solve an absolute value inequality when it's less than a constant, like in this case, my constant was 2, we set whatever's inside the absolute value between C and negative C, right? So 2 and negative 2. But if we just call it C in general, and this is what I mean. So look, let's go back to the notes. If we're going to solve the absolute value of U, let's just call it, is less than C, it's going to be all the numbers such that U is between negative C and positive C, just like I showed you on the example on the whiteboard. We're just generalizing here with U and C. I used X and 2 in my example, right? So look, let's do a couple of examples, and we're going to do less than for each example here. Let's practice absolute value less thans. So look, in A, we want to solve the absolute value of X less than 8. So X has to be greater than negative C, or 8, right? Negative 8, but less than C, which is 8. Right? So every number that's between negative 8 and positive 8 has a distance that's less than 8 units from 0 on a number line. And if we were to put this on a number line, here's 8 and negative 8, my solution set is going to go from negative 8 to positive 8, and it's going to be everything in between, but not including 8 and negative 8. So every single number in between negative 8 and 8 has an absolute value that's less than 8. And if I want to write this in interval notation, we would write negative 8 to positive 8, not inclusive. So open parentheses. Let's look at B. So we have the absolute value of X plus 3 is less than 6. And this holds true whether it's strict or if it's, inclusive, meaning a less than or a less than or equal to. It's this, you would just use a closed bracket. So the absolute value of X plus 3 is less than 6. So that means whatever X plus 3 is, it has to be between negative C and positive C, where C is 6 in this case, right? So it's going to be between negative 6 and positive 6. So we have a compound inequality, right? So let's solve for X. So I'm going to subtract 3 from all sides. So we have X is greater than negative 6 minus 3 is negative 9, but less than 6 minus 3, which is 3. And if I want to write my solution set on a number line, it's going to be everything from negative 9 to positive 3. We're going to shade in between. And if I want to write this in interval notation, we're going to go from negative 9 to 3, non-inclusive. And let's do one more. And you know what? Because I want you to see it's going to be the same. Instead of less than for C, the absolute value of 3x minus 6 is less than 18. Let's just make it less than or equal to. So I want you guys to stick the little equal sign underneath. So let's solve this. So 3x minus 6 has to be greater than or equal to negative C, or negative 18, but less than or equal to C, or positive 18. So I have a compound inequality, so I'm going to solve for x. Let's isolate x. So I'm going to add 6 to all sides. So I'm going to have 3x is greater than or equal to negative 18 plus 6 is going to be negative 12. And less than or equal to 18 plus 6, which is going to be 24. And now let's divide everybody by 3. So we're going to get x is greater than or equal to negative 12 divided by 3 is negative 4, or less than or equal to 24 divided by 3, which is 8. So on a number line, we're going to put a closed circle now on negative 4 and positive 8. And we're going to shade in between. So my solution set is everything from negative 4 to positive 8 inclusive. And I would put closed brackets, the square brackets, around the negative 4 and the positive 8. And again, you could always check your answers by picking values that are within the shaded area, right? And it should make a true statement when you go and plug back into the original. And if you pick any values that are outside of your shaded area on the number line, they shouldn't work when you go to plug it into the original inequality. So that's how we solve absolute value inequalities that are less than or equal to. We solve for u, or whatever the expression is inside the absolute value, is between negative c and positive c. So now let's look at what happens if we change the direction of the inequality. So before we look at example 5, let me go back to the whiteboard for a minute. And what if I said to solve the absolute value of x now is greater than or equal to 3? So now we're doing greater than or equal to. So again, I always think it's nice to look at a number line. So the absolute value of x has to be greater than or equal to 3. So what that means is the distance that x is from 0 on a number line has to be 3 or more. So all my solutions have to be a distance of 3 or more away from 0. Well, here's 3, right? And negative 3, both those values are a distance of 3 from 0 on a number line. So they're included, right? Because the absolute value of x can be greater than or equal to 3. But now where is the distance greater than 3 or more than 3 away from 0? Well, it's everything this way, right? All these numbers are more than a distance of 3 away from 0, right? And then all these numbers to the left of negative 3 are also a distance of more than 3 away from 0 on the number line. So now look at my solution set. It's going to be all values of x that are less than or equal to negative 3, or all values of x that are greater than or equal to 3. So x is less than or equal to negative 3, or x is greater than or equal to positive 3. So if we generalize this and go back to the notes that I have, The solution set of the absolute value of u now being greater than c are the numbers that satisfy u being less than negative c or u being greater than positive c or c. And that's exactly what we had in this example that I showed you on the whiteboard, right? Just think of u as the x and c as the 3, right? So x is less than or equal to negative c or negative 3, and x or u is greater than or equal to c, or 3 in this case. So that's how we solve an absolute value inequality when the inequality is greater than or equal to. We're going to solve it this way. So let's look at example 5a. And you know what? Just so I don't have to keep scrolling back and forth up here, let's just write this rule right here. So if we want to solve u, where the absolute value of u is greater than c, then my solution is going to be that u is less than negative c or u is greater than c. So example 5a says solve the absolute value of x is greater than 4. So my solution is going to be that x is less than negative c or negative 4, or x is greater than c or 4. And on the number line, it's going to look like this. We're going to have an open circle on 4 and negative 4, right? And x could either be less than negative 4, which is everything to the left of negative 4, or x could be greater than 4. So I'm going to shade everything to the right of positive 4. So the way I'm going to write this in interval notation is, let's look at the interval on the left. We're coming in from negative infinity to negative 4, but open, right? Open parentheses. And then I want to join it with the other shaded set that I have up here to the right. So I'm going to use my union. And now we're going to go from 4 to infinity. So that's how I could write my solution in interval notation. So here it is visually or graphically on a number line, and then right below it, I have interval notation. So let's solve B, and you know what? Let's make it a greater than or equal to. Put the little equal to underneath. So the absolute value of x plus 2 is greater than or equal to 6. So we're going to do the same thing that we did in A, except now u is going to be x plus 2. So we're going to take x plus 2 and set it less than negative c or negative 6, or x plus 2, and that should be less than or equal to negative 6 because this is inclusive, or x plus 2 is greater than or equal to c, which is 6. And we have to solve both of those inequalities. So if I solve x plus 2 is less than or equal to negative 6, I'm going to subtract 2 from both sides. So I'm going to get x is less than or equal to negative 8. Or solve the one on the right, x plus 2 is greater than or equal to 6. So I'm going to subtract 2. And I'm going to get x is greater than or equal to 6 minus 2, which is 4. So on a number line, if I shade x less than or equal to negative 8, negative 8's included, right? So closed circle. And I'm going to shade everything to the left. And we're going to put an arrow indicating we're going to shade all the way towards negative infinity. Or x could be greater than or equal to 4 also. So I'm going to shade everything to the right of 4, including 4. So I have my closed circle. And my solution set as an interval is going to be negative infinity to -8, including the -8. Union, now we're going to go from 4 to infinity. And let me show you why this makes sense. Look, pick a number that falls within this interval for my solution set. 5, right? 5 is within this solution set. If I go to plug it into the original, I'm going to have the absolute value of 5 plus 2, which is 7, right? Is greater than or equal to 6. Let's pick something like 0 that's not in my solution set. If I go to plug 0 into the inequality, I'm going to have the absolute value of 0 plus 2, which is 2, is greater than or equal to 6. That doesn't make sense because 2 is not greater than or equal to 6. So I just want you to see how you put this in perspective, right? In terms of realizing that the values that we shaded on the number line satisfy my inequality. So when I pick any of these numbers in the shaded region on the number line, it's going to make that inequality true. But if I pick something that's not in the shaded area, right, that doesn't fall within this solution set, it's not going to make sense. Now let's do one more. Look at C. So the absolute value of 2x minus 4 is greater than 10. So since we're greater than, and we have an absolute value, we're going to take u, the expression inside, which is 2x minus 4, and we're going to set it less than negative c, or negative 10. Or another possible solution set is u, which is 2x minus 4, is greater than c, which is 10. So we have to solve both of these. So the one on the left, I'm going to add 4 to both sides. So I'm going to get 2x is less than negative 6. And I'm going to divide by 2, and I'm going to get x is less than negative 3. Or, now let's solve the other one. So I'm going to add 4 to both sides, and I'm going to get 2x is greater than 14. Divide by 2. And I'm going to get x is greater than 7. So my solution set is anything less than negative 3 or anything greater than 7. And that's what that would look like on the number line. And if I want to write interval notation, we're going to have negative infinity to negative 3 open, union, open from 7 to infinity. And that's how we would solve an absolute value inequality when it's greater than or equal to.